So, okay, a few announcements before we start with the exam next week, next Thursday. It's an evening exam. So, we will have class in the morning. We may do some review kind of stuff. The exam is going to be in this room at 7. So, some of you had made requests for makeup because of a conflict. If you can provide me some documentation explaining the nature, I will be happy to arrange it. If you need any accommodations, if you're registered with disability services, you need to let me know this week. If they require that I send them the exam several days in advance. Okay? So that's the exam. I will do a review next week. I will also put up a sample exam on Moodle that illustrates what kind of questions you should expect on the test. Okay? The other announcement was the homework. I sent email about it. I extended it to Monday. So some of you asked for a little more time given the lab and so on this week. So it's already on Moodle with a new due date of Monday. Okay? So those, yes.
Will we have discussion the day after the exam?
Will you have discussion? I think this you always have discussion. What we'll do there, we'll see, but yes. Okay, so I'll continue where we left off from last time. So what we are going to do today is basically look at how to use some of the synchronization primitives. We have looked at locks, semaphores, monitors, and try to solve some real problems, real world problems. And we have looked at producers and consumers. We started talking about readers and writers. I'm going to show you how to solve readers and writers today, and then we will look at one more example called dining philosophers. Okay, so those are three good illustrative examples of how you can use monitors, locks, semaphores to solve some problem or the other that you encounter when you need to do synchronization. Okay, so just to recap the discussion from last time, we were talking about this notion of a read-write lock. We generalize this from a normal lock. Okay, and a normal lock, regardless of the operation you want to perform, whether it's a read operation or a write operation, you have mutual exclusion. Everything else is blocked from accessing that data structure while the thread that holds the lock is accessing it. Okay, and we said that may be restrictive in scenarios where you have some readers and some writers. In the scenarios where you have only readers, you don't need a lock at all. We discussed this last time. Okay? But if you have some readers and some writers, what you would like is optimization to this notion of a lock, where if there are only readers, you can allow concurrence. You can allow more than one reader to read at any given time. Okay? At the moment there is a writer trying to write, you should fall back to your mutual exclusion where no other thread can read or write while this write is actually in progress. Okay? So that's basically the reader-writer problem. So we will look at how to solve this problem today, and here is how we are going to formalize it. Okay? So in terms of our correctness criteria, so we should allow both reads and writes to happen within critical section. Okay? Just because if there are only readers, you do not actually need a lock. That's because we may have writers as well. We'll just put everything in a critical section, but we will guarantee mutual exclusion for writers. When there's writers, there should be mutual exclusion, but we will allow multiple readers to enter the critical section. Okay? At any given instance. So rather than having only one thread, if you have only reader threads, multiple threads can enter the critical section. So we want to write code that basically gets us all of those properties. Okay, so I'm going to show you some ways to solve this problem, but I would like you to also understand and try to come up with ideas on how you can do this as well. So here is one implementation. Okay? This is going to be a reader-writer solution using semaphores. Okay? We are going to use two semaphores to solve this problem. There's a mutex semaphore that's simply going to act as a lock. Okay, so it's no different from a lock. And then we also have another semaphore called the write semaphore that is going to control the first reader or the first writer, and depending on whether it's a reader or writer, different things will actually happen. Okay? So before we even start with the solution, let's try to see how one can go about solving the reader-writer. So what should we be doing to get the properties I just described on the first slide? Okay, so intuitively, how will we solve it? So let's not worry about what we will do with semaphores and locks and whatnot. Yes.
Well, we should only lock it when the writer goes into it. So we have statements that we can catch when the writer goes in. Don't have that same restriction with readers.
Okay. So we should only block when writers go in and let multiple readers enter. Okay, so that's basically a suggestion on how we can solve the reader's writer problem. So the question is, how do you actually do that? How do you make sure that you are going to only block when there are writers, but not block when there are only readers? Yes.
Have different locks from two.
You are going to have different locks for the two. Either you have to acquire the lock in mode, which said I'm trying to get the lock in read mode or write mode, or you basically say give me the read version of the lock or write version of the lock. Okay, so the lock is going to behave differently depending on whether it's a reader or writer. So you want to distinguish between the two. Okay, you want to treat readers and writers differently. So you want to be able to first make sure that you know whether when a lock is being acquired, is it a reader acquiring the lock or the writer acquiring the lock. So the two ways to do this is to specify, do you want the lock in read mode or write mode? So you pass an argument to acquire, saying I want the lock in one of these two modes, or you have two methods, saying get read lock and get write, something along these lines. Okay. So now let's look at one solution, and then we'll look at many different solutions that do slightly different things. Okay. So here we have now a read lock and a write lock. So the read method is going to get the lock in read mode. The write method is going to get the lock in write mode. Okay? And the write method is very simple. It is going to look exactly like mutual exclusion. It is going to do a wait. Okay, write.wait, which is basically going to acquire the write lock. It's going to perform the write, and then it's going to do a signal. Okay, that's just what a semaphore does. Is the write.wait is acquire, okay, equivalent to lock acquire, write the signal is going to release them. Okay. So when a writer is writing, okay, it's going to simply get the lock as a mutual exclusion. Okay, so I'm just going to block it. So let's look at what the readers do. Okay. So here is basically code for the readers. Okay. So you are now going to first do a mutex wait, which is we are going to get a lock. This is not the lock on the data structure you are reading or writing. This is simply a lock on a counter that tracks how many readers exist in the system. You will see that there's an integer counter called readers. Okay, when the first reader or whenever a reader comes in, you have to increment the counter. Okay, because that counter is a shared data structure, you have to protect it with a lock. So this mutex is protecting the read counter, it's not protecting the actual reading itself. This actual reading is not protected by anything in this case. So we are going to do a mutex wait, which is going to get mutual exclusion, increment the number of readers, and then we see if you are the first reader. Okay? So if number of readers equals 1, that means you are the first reader to enter the system. At this point, you should block all writers, okay, because there are reads in progress. Okay, you have to wait for all the reads to finish before the writer actually can start. Okay, otherwise, you are going to have a problem. So the way you are going to do block all writers is you are going to do a wait on write. Okay, this is a semaphore. It's initialized to 1. So as soon as you do a wait, it will decrement to 0. If a writer comes along, it's also going to do a write.wait. It's going to block because that will take the value to -1. Okay, so that's how semaphores behave. So remember, wait decrements and signal increments. When you do a wait and it decrements and it turns negative, then we block. So if you're the first reader, okay, and the write is value of the write semaphore is 1. If you look at how we initialized it previously, you'll see that the write value was 1. Okay, so if the first reader comes along, it does a wait, that value goes to 0. Okay, the reader doesn't block, but in doing so, if it will prevent any subsequent writers from being blocked. Okay, so the idea is whenever the first reader comes in, it should block all the writers, and whenever the last reader leaves, it should unblock writers. Okay, so that's essentially what's happening. So you'll keep a counter to track whether you're the first reader or not the first reader. So you always increment the read count. If you're the first reader, you block the writers, then you release the lock that on this counter, then you perform the read. Okay? And then you do the opposite when you are done with the critical, not the critical section, done with the reading. Again, grab the lock and decrement the number of readers. If you are the last reader, you are going to enable writers by doing a signal. Signal will increment, or if there is a writer block, it will let it go forward. Okay. Okay, so any questions on this? What part of this should I go into more detail? There are several subtleties that we haven't discussed. This is the basic code.
Wait, so does the mutex just act as a normal lock?
The mutex acts as a normal lock. The only thing is it's not protecting the read. So you'll see that you acquire and release here, the read is unprotected because you'll have let multiple readers go in. Okay? So only protecting this counter, which is the read count, reader count. Okay? Okay, so let's try to analyze a few different scenarios. Okay, let's assume that the writer comes along and is doing a write. Okay, now a reader comes in. So what happens in this case? Okay, so the writer is basically performing the write. The thread is actually in there, in that function there. Okay, now a reader comes in. Clearly the reader has to be blocked. Okay, so the question is, how does that happen? Yes?
Reader is going to increment the count when it gets into that critical section, and then it's going to equal 1, so it's going to wait for the writer.
Okay. So what does the reader do? You just have to go through the code and see. So you have a writer writing. The reader comes in, it does mutex.wait, it gets this mutex lock, increments the number of readers. Okay, it's the first reader in the system. It says, am I the first reader? Yes. Okay, you are going to do write.wait. Okay, as originally I said, this is put in place to block the writer, but it actually serves two purposes. Okay, if there are no writers, write.wait is going to block a writer. But if there's already a writer, that writer has done the wait and is performing the write. So that has made the semaphore value go to 0 already. Because wait has decremented the semaphore. If you do a second wait here, this will take the value negative and block the reader. Okay, is that clear what I just said? Okay, there are two scenarios here. If the reader comes in first and does the first wait, any subsequent wait will block, so a writer will block. If the writer comes in first, okay, the reader is going to be executing the second wait here. Okay, the writer executed the first wait, will do a second wait, this blocks the reader. So in essence, the writer will block readers from entry. Okay, this is the first reader. So reader blocked. Now let's say ask what happens if the second reader comes along. Okay, because that check is only done by the first reader. How do subsequent readers get blocked? Yes.
Subsequent readers just get to mutex.wait, and they have to wait because the first reader is the signal to mutex.
Reader will block on mutex. Anybody else have any other?
Which case are we talking about?
So we have, the case is writer is in, right? So this is a scenario. So writer comes first, okay, he's doing the write. Then the first reader comes in, it's blocked. Okay, it's blocked here in particular. So if the first reader, it does a wait and it gets blocked. And now the writer is still performing a write. Let's say second reader comes along. Okay. Question is what happens to that reader? It should also block because the writer is still performing writes. It should block everything, regardless of whether it's a read or write. Okay. You know, all I was pointing out was the first reader blocked because it checked the read count. It was the first reader and it performed this wait. No other reader will actually execute this statement because the read count is already 1. It will go above 1. So the question was how do readers block, and the suggestion was there's a mutex that's going to block. Anyone have anything to say? You agree or disagree with what was said? Did you understand what is going on in terms of the subtleties of what the readers and writers will do? something like that.
Well, since the first reader is still waiting inside the critical section, the second one won't get inside the critical section until that one's done.
Okay, so the same thing is being emphasized. So the first reader is blocked here. It holds a new text lock already, and it's blocked in the critical section. Second reader comes in, it will actually get blocked at the new text itself. It won't even be able to proceed because that new text is already held by the first reader. So all subsequent readers will block on the new text as they should. So the writer will not only block the first reader, it will block all the other readers. It should be clear the writer will block other writers as well because all of those writers will come and block on the right weight. They will block on the first statement of the right function. Okay? So writer is going to guarantee mutual exclusion. It will block out all of the readers and all other writers. Okay, is that clear? Now let's look at other scenarios where readers come along and see what happened to the writers and so on. Okay, so we'll consider the opposite scenario. Okay, let's say a reader comes in, okay, there's no writers at this point, so the reader is going to go in, increment, read count, it is the first reader, it's going to do a wait on this semaphore, that's going to take the value from 1 to 0, okay, and it will proceed. Okay, you go and start reading. Yeah, what does the second reader do? Let's say now second reader comes along. Yes?
It'll go through the mutex lock, have that, and then so that'll call wait. It'll up the reader by 1 since it's not the first reader. It'll wait on the WRT lock, and then it'll release the mutex lock.
Okay. So the second reader is going to just do a mutex wait. Okay, the first reader has released the mutex here. It's busy performing the read. Second reader comes in. It's going to grab this way of mutex. It's going to increment the read count. It's going to go from 1 to 2. Okay, it's going to skip the if. And there's nothing to do. It's not the first reader. It's going to release the lock. So all it does is it increments the read count and it goes and does the read. Okay, so it's not blocked. In other words, so you have now two readers that have entered the read method. Okay, they are all doing this concurrently. So you should see that any number of readers can come in. Okay, they will each go into that mutex wait and simply increment the read count. They will exit and start performing the read. So you are getting concurrency. Multiple threads have entered the critical section. This is not mutual exclusion. Okay, so you are actually allowing multiple threads to perform the read at the same time. Okay? Any writer that comes in while these reads are happening will just block that because the first reader did a wait here. Okay, so that's going to cause any subsequent writers to block. Okay? Any questions on this? So we looked at two scenarios. Writer comes in and then what happens to all the readers. And we saw that all the readers will block except that the first reader will block on that wait, the other readers will block on the mutex. And when readers come in, they all are allowed to go into the read method and they block the writers. Okay, so that's implementing read-write locks using semaphores. And before we proceed, we'll see, do we like this method? Is there anything wrong with it? Not from a correctness standpoint, but from another perspective.
Well, if you have a reader in the second portion where it takes the mutex,
Yeah.
and then another reader and a writer both come in,
Okay.
and they're both waiting,
Okay.
then you would unlock the writer, and then also unlock the reader.
Okay,
So when
so
they go to
let's repeat your scenario. So you have a first reader is in this part of the code. It is trying to decrement the read count. So now what happens? What was the scenario you were?
Also, right now, both mutex and write would be locked.
Yes.
But if you have both a reader and a writer come in at the same time,
Yep.
it would unlock the writer after it does if readers equals 0,
Okay.
and then it would also unlock the reader.
If you unlock the writer here, so the reader has basically already unlocked the writers here. If you have the last reader to leave, you are going to unlock the writer. Okay? So now if a reader and writer both come in, they are going to compete. Depends on who goes first. Okay? If the writer goes and executes the wait, it's going to decrement it first and the next reader, because the the read count has gone back to 0, the next reader will block here. But if the reader goes first, because that's completing, they just happens to be scheduled first, if you do this wait first, then the writer is going to block. Okay, so it's just going to be a condition race to see who gets the right mutex first. Okay, so yes.
I was going to say another issue is if you have a steady stream, a steady stream of readers, you can starve your writer.
Okay, so the point being made is there could be starvation here. So you have a reader that has come in, okay, it's blocked the writer, okay, is doing a read. Okay, now if there's a steady stream of readers that are going to come in, the read count is never going to go back to 0. Okay, so all writers are now blocked. Okay, so if you have a busy system and there are lots of readers, okay, there is always a reader in the system. Once the first reader goes in, the read count will never go back to 0. So you are going to starve the writers. Okay, so this solution is correct, but it has a starvation problem. Okay, it favors readers over writers. If readers, there are lots of readers, you will not allow writers to proceed. Okay, nothing bad will happen, but you will have starvation, which is also bad, but it's not going to be a bug in the code. It's simply a bad scenario you have to deal with. Okay, so here is a solution now that is going to do the opposite. Okay, so and then we'll see solutions that actually try to balance and be more fair to both readers and writers. They get processed in the order in which they come in. Okay, so this solution is going to favor writers over readers. So here is the right method. It looks a little more complicated, but it's not as bad. So you are going to have now a read count and a write count. Okay, so the first writer that comes in is going to increment the number of writers. Okay, and then it's going to basically block all the readers at this point. Okay, so it explicitly do a read block semaphore and block all the readers. Okay, and then it is going to grab a lock to perform the write. So this is mutual exclusion. So this is basically the writing that's happening. Okay, any other writer is going to block here because you have to grab the lock. Okay, so you block all readers, you block all the writers. Okay, and then you decrement the number of writers, and when the number of writers go to 0, you unblock the readers. And now we'll look at the read method, and then we'll try to understand how this works. Okay? So what we have done in the writers is we're also now tracking the number of writers. In the previous example, we were only tracking the number of readers. Okay? The writers just basically competed for the lock and just went in as and when they got the right lock. In this case, or the right semaphore. In this case, we are also going to track the number of writers as well as the number of readers. Okay? So basically what has happened here is in the read method, you are going to do a write pending dot wait. Okay, so that semaphore, so there are lots of semaphores here. As you will see, there are 5 or 6 different semaphores. They do slightly different things. So the write pending semaphore, what it is doing is, if there is, it checks whether there is a pending write. If there is a pending write, then it only allows one reader to go. Okay, so essentially what we have done is you can have read concurrency. Okay? If there are no writers, let as many readers as there are in the system go ahead and perform reads. But the moment a writer comes along, okay, you block additional readers from proceeding. You let all the readers that are already there, let them finish, and then let the writer go. Okay, is that clear what I just said? So this also you can look at this picture to understand what's happening. Okay, so let's say there's some random order of readers and writers. Okay, each of this is a thread, and let's say that's tied. So in our first solution, so there's a reader thread, writer thread, reader thread, and so on. So in the first solution, what happened is the reader, this is the first reader, it came along, it was allowed to proceed. Another reader comes in, it's allowed to proceed. These two readers are still performing read, writer comes along, it's blocked. Okay? The reader comes along, it's allowed to proceed, it's allowed to proceed, and so on. So there's a steady stream of readers, okay, that are all entering, but because there's always a reader in the system, it's not allowing any writers to proceed. So the writers are starved. Okay. In this example, what has happened is the following. So, use a blue marker. The first two readers get to go. Okay? The moment a writer comes in, it increments the write count, saying I am pending write. So you are going to block, waiting for these readers to finish. But by blocking it, we are also tracking the number of writers. It also blocks any subsequent readers. Okay, so it says there's a pending write. So any subsequent readers are not let in. And you just wait for these reads to finish. Then you let this writer go. The writer is going to finish. Okay, so these two are done. Then the writer goes, it's going to finish. Then it's going to unblock all the readers. So the next 3 readers get to go in. Okay? And then this writer comes along. So these 3 go in. The writer comes along, it's going to block, waiting for the reads to finish. But it will also block all subsequent arrivals. Okay? So the basic idea is whenever a writer comes in, it blocks everything else that comes in after it. So that it gets some favorable treatment. You don't just let reader jump over a writer and enter the system. Yes.
So you have the opposite problem, if you have a lot of writers with that sort of thing.
Yes. So the point is, if you had a lot of writers, you are going to start. That is why I said this is not going to solve the problem. This is just flipping the problem. So you favor writers over readers. Okay, to be fair, you have to basically do both. Readers should block any subsequent writers, and writers should block any subsequent readers. And then you have fairness. You have less concurrency. You will see that when these 2 reads are taking place in the first solution, you let other readers go in, you got more concurrency for reads, but you had less fairness. So it's a trade-off. You have to ask, are you going to put up with more performance but occasional starvation, or are you going to actually try to be fair but at the expense of reduced concurrency? So because there are reads, you're blocking other readers even though they could have gone and then finished the read. Okay, is that clear what we are trying to do here? The read-write locks. Okay, so I will show you some other solutions that are easier to read than this, because this one looks like there are lots of different things happening. Okay, so now we'll try to do this in Java and we'll try to see what's going on. Okay, so this is readers writer using Java, okay, and monitors. So you're going to simply use a synchronized method to do this. Okay, so here is our read method. Every reader has to execute this code. It basically has to call this prepare to read method, which is here. Okay? It has to do the reading and it has to call the done reading method. Okay? So you will note that this method is not synchronized. Okay? If you made that method synchronized, you are going to block other readers. Okay? So the read method shouldn't be synchronized. Okay? So now the first thing that a reader comes in and does is prepare to read. What you're doing here is simply prepare to read. You're going to check, is there a writer already waiting? Okay, this is trying to be more fair. So you say, although you're a reader, okay, you say the first thing you check is there some writer ahead of me? There's a writer ahead of me, I'm going to play nice and block. Even though I could have gone ahead, if there's some other reader, I can just jump over this writer. But you say, if there's a writer, the number of writers is greater than 0, you're going to block. Okay? And then increment the read count. If there are no writers, then you're going to increment the read count and enter. Okay, so it should be clear if there are no writers in the system, neither a pending writer nor an active writer, you're simply going to increment the read count and go in and start reading. So there will be concurrency, full concurrency if there are no writers at all. Okay, the moment a writer comes in, the writer blocks and so do all subsequent readers. And in the other method, once you are done with the reading, you call the done reading method, you do the opposite, you decrement the read count, and when the read count goes to 0, you unblock. You do a notify and you unblock the first one that is actually blocked on that condition variable. Okay, that wait is a condition variable. Okay, so as we talked about last time. Okay, so that's the read method. We haven't seen what the writers do, but this is what the readers are going to do. Is that clear? When I go on to the next slide. Yes, please. Okay. What will that do for that example? Is that your question?
Yeah.
Okay, so in this case, what's going to happen is, here is this. Okay. Reader 1 comes along. Okay, it's going to call prepare to read. Number of writers at this point is 0. There are no writers. Okay. So it won't do anything with this while statement. It's going to simply increment the read count, go and start reading. No blocking. Okay. So it's going to go ahead. Reader 2 comes along. It's going to call prepare to read. It's going to call that method. There's still no writers in the system. we'll increment the read count, go into read. Okay. I haven't actually shown you the written code, but when this writer comes along, it has to block if the reads are still in progress. Okay, and we look at that. Okay, so this should block. But now that the write count has become 1 as a pending writer, when the next reader comes along, it will actually check. There's more writer count is more than 1, it is going to block you. Okay, so it's going to say there's a writer ahead of me. Okay, so I should be nice and not jump over. Okay, otherwise, you could have just incremented the read count. If this statement was missing, you would have incremented the read count and simply gone and read. That would have started the writer. So you're trying to do the right thing and you're going to block. Okay, so that's basically how it's done. Questions on that? Okay, so here is the write method. It's going to basically also track the number of writers. So first thing to realize is this is our write method. Okay? And it is synchronized as it should. That means that only one writer gets to even execute this method at any given. There is mutual exclusion. So that read method was not synchronized. We wanted multiple readers to actually enter. Okay, so this method is not synchronized. Do realize, however, that prepare to read and done reading are synchronized methods. Okay, so those two methods are synchronized. Okay, you should ask why are they synchronized, but the read method is not synchronized. Yes.
Are you asking why?
Yeah.
Because those two methods change a shared variable, and you don't want more than one at the same time.
Okay. So these synchronized methods are simply protecting the counter that is being modified. Okay, that's a shared variable. Some thread may be decrementing, other threads are incrementing. So you don't want to mess with that. Okay, so you want to protect it by a lock. So you make those methods synchronized. The read method itself is not synchronized because you want, once you have modified the counters, you want reading to be concurrent. Okay, so this method is not going to be synchronized. It just calls two smaller synchronized methods that just protect the counters. Okay. Now, as opposed to that, you will see that the write method itself is synchronized because you want the whole thing to be mutually exclusive. Okay, so only one writer should even enter this method at any given time. So you already block them at this level. Okay, only the first writer gets to go in. It's going to call prepare to write, which is going to increment that write count. Okay, and then it checks if there's some reader already reading, you can have to block. So that's exactly this scenario where there are two readers in the system. First writer comes along, the write count goes to 1, read count is 2, so this writer is going to block. Okay. Now because it has incremented that write count, any subsequent reader will block also because the write count is 1. So we say there's a writer ahead of me, I should block. Okay, so the writer blocks waiting for the first two readers. Because the writer is blocked, any subsequent readers will block on the writer. Okay, so we are trying to achieve a more fair scenario in terms of read-write blocks. Yes?
Wait, so when a reader or a writer in a synchronized method, neither readers nor writers can enter any of their synchronized methods also?
Yes. Synchronized, in this case, it at a class level, it's a global lock. Okay, so everything else is going to block. Okay, so you will basically just increment the writer with just a reader ahead of the block, and then in the done reading part, you are going to decrement the writer and just if there anybody sleeping is being done. Okay? So you will see now that this method is synchronized. As I said, so only one writer gets to go. If another writer came along here, it will block right here, it won't even go in. Because it needs to get along, the first writer is actually in here and it is sleeping. Okay? Now you should also ask the question, why are the prepare to write and done writing method not synchronized? Okay, so in the previous case you will see that prepare to read, okay, this method is synchronized, that method is synchronized. Okay. In this case, they are not. Why? Yes.
They're only called within the synchronized method.
Okay, so they are called from a synchronized method. So there is no need to make them synchronized. You agree with that? What would have happened if you made them synchronized?
Wouldn't that just calls up in the block, especially compared with like one, because eventually if there's a synchronized math method, there's a global lock on all the readers.
Yeah.
So once it hits the second, the while loop, and it wasn't read, like, if there was another reader not equal to 0, it would wait, and then the entire system will hold this.
Okay. So just to generalize what was said, if one synchronized method calls another synchronized method, you are going to be in trouble. Doesn't matter what the code is. Okay? First synchronized method already grabbed the global lock. It calls another synchronized method. Implicitly, when you call any synchronized method, the first statement is going to be lock acquire. You already hold the lock, you're trying to acquire that lock. Okay? The lock is in use, so you will block yourself. Okay? So it's always going to be a problem if any synchronized method calls the second synchronized method. That should never happen if you've written correct code. Because you hold the lock, you're trying to grab something you already hold and you'll block yourself and block forever. Yes.
How does notify know which lock?
Okay, how does notify know which one to wake up? It doesn't. So you can actually wake up. This doesn't specify what to wake up. That depends on the implementation. So internally, if you have a queue of threads that are sleeping, notify will wake up the first one. That's an implicit assumption. So if there are multiple of these threads that are sleeping on that condition variable, and if you have internally you put them on a queue, notify will wake up the first one. But that's implementation dependent. You're absolutely right that we didn't explicitly wake up any particular thread. We just said wake up some thread. And our assumption is that the implementation is written in a way that is going to make up the first thread that's left, just for fairness. If you don't have fair implementation, you will not get that property. So we are just assuming that it will just make up the first thread. And that's because that's how they are internally implemented condition. You have a queue of 18 threads, and then you just look at the head of the queue, and that was the first one that you make that up. Okay, so several things to keep in mind. Okay? Don't call synchronized methods from other synchronized methods in any Java. It's a very bad idea. It's never going to work. Other things here are this is a much better implementation than the first two that we saw because you have some fairness and the loss of some concurrency. Okay, because there may be readers that are reading, if write comes along, it blocks subsequent readers. That reduces the concurrency of the reads. You could have let them jump over the writer and have more concurrency, but that would not have been fair to that writer. And you may have actually starved the writer. So you're trying to prevent all of those problems. Okay, so you try to balance these two trade-offs, fairness and concurrency of the reads. Okay, yes?
What happens in this code when a writer is done and there's writers and readers waiting?
Okay, that's a good point. So you can ask what happens in the code when the writer is done and then there are readers and writers waiting. Okay. So we can look at the code and see what is happening. So let's say first two readers are done. This writer is now currently writing these all are blocked. So you'll see what happens when you're done with the writing, you call this done write, it decrements the write count, and it just calls notify. Notify just is a condition variable. It says if there is any thread that is asleep, as another wake those threads up. In particular, we know that there are, in this case, 3 readers and a writer asleep. Okay? So if the implementation is fair, these are all in a queue. Okay, this is your wait queue. Okay, for the condition variable, you have thread 1, thread 2, thread 3, they are all waiting. Okay? Let's say they're waiting in this order. So that notify is going to wake up the first reader. Okay? So it's going to basically wake up that reader, which was, so the first reader was blocked here. Okay, basically I checked that there's a writer and it was doing waiting. So the first reader wakes up, okay? It increments the read count, it goes in. Okay? Now what happens to the second reader? So this writer is done. Okay, all of these threads are blocked. You unblock the first reader. How does the second reader wake up? Yes, that's something.
When the first reader is done, since there's a writer that's waiting.
Okay, is the writer waiting? The writer is waiting, but what is it waiting on?
The reader. If it did work.
So you have to realize that all these threads are waiting on different things. Okay, so this is the first thing to keep in mind. There are 3 readers and 1 writer that we said were all waiting. The first reader is blocked here. Okay. Where is the second reader blocked? Yes.
when the method is called.
Second reader is blocked on that synchronized. So that's the lock acquire. Okay, the first reader is actually blocked here, so it's going to block the second reader there. Okay. Where's the writer block? Yes.
Wouldn't the first reader also get stuck trying to call the method because the writer holds the synchronized lock?
Okay, so the writer is going to call synchronized. So that's why all the readers are blocked there. All the writers are also blocked there. Okay.
But you said that the first reader would make it to the wait.
Oh, yes, so you're right. So in that, if this reader had actually come just before, it would have been blocked. In this case, you're right, it will all be blocked in the synchronized. You're right, I take back what I said. In fact, if the write is actually in place, you are holding a global lock, so no readers have even gone ahead. So all the readers are blocked here. You're absolutely right in that case. So all the readers are blocked here and all the writers are also blocked. So the first reader is going to go in and it's going to basically block a subsequent writer because it's going to see that the write count is 0. Okay? And then it's going to go in and execute. And then since it releases that lock, the next reader gets to go in and so on. Okay? So these 3 readers are going to go in and all start reading. This writer gets blocked because the first reader that went in blocked it. Okay, it was blocked there, but now it is going to go and block on the wait itself. Okay, is that clear?
It still holds the global lock even if it's in a wait queue, right?
No. So if it's doing wait, that's a condition variable. If you remember, the definition of condition variable is you go to sleep and you release the synchronized lock. So if you're there, you're not holding the lock. So yes, so the point I was saying was that was not right. The first reader was not blocked on the wait, it was blocked on the synchronized. Because the writer had actually got the global lock. Okay, is that clear? What happened? Yes.
Wait, so at what point does the synchronized, like, the global lock get released at the end of the method?
Yes. So implicitly, whenever you exit a synchronized method, it's released. When you're in the synchronized method, you hold the lock.
So when in the next one, when it's done writing, wouldn't it notify before it releases the global lock?
Yes. So you have to realize what the notify is doing. So you are saying you have this notify, right? The first writer comes and does a notify. That only wakes up threads that are asleep on a condition variable. Okay. So this thread could be asleep on the wait here, or it could be blocked on the lock acquire here. So if you do a notify and there's nobody waiting on the condition variable, there is nothing to do. In this particular scenario, because you had a global lock, everyone else was blocked at that level. Nobody could even enter the critical section to block here. So that notify does nothing in this case, in this particular example. Right, so in this case, this notify is not going to have any effect because there's no thread asleep on a condition variable. They're blocked just getting the lock itself. Okay, so there's nothing was going to happen because of that notify. So that notify will only work if there's a reader actually blocked here, okay, which was not the case in our case. So any other questions here? So there are lots of subtleties in terms of what happens when the reader comes first and some writers come along, and a writer comes first and some reader comes along. So the easiest way to understand is to actually work this out. You basically have a queue of arrivals and then see what gets blocked where and who gets to go in, etc. And then you'll understand how the code works. We looked at least 3 different scenarios. Okay, so that should give you some sense of how the system is actually working. Okay? Any questions here? Okay, so we will move on to, okay, so read write lock. So now the good news is, having said all this, if you have to actually use read write locks, you don't have to implement your own. What we looked at is actually a implementation of a read write lock. Okay? This is supported out of the box by any system that supports synchronization. So in Java, if you wanted to use a read-write lock instead of a normal lock, you would just call a read lock or a write lock. Okay, so that method internally implements what we just showed you in the previous slides. Okay? If you're writing C code, you want to use read-write locks, you simply call a pthread read-write lock. So instead of declaring a normal lock, you declare a read-write lock, and you can acquire the lock in read mode. Okay, so you get a lock as a read lock, or you can acquire the lock in write mode. Okay, and unlock is still the same. Okay, so there are two types of acquire for a read-write lock: a read lock and a write lock. Acquire. Okay, unlocks it in either of those two modes. So if you are actually using code that needs read-write lock, you do this. If you are a library designer who is writing a read-write lock, you do what we showed you on the previous slide. So that tells you how they are actually implemented internally. Okay? Yes, questions?
So if we use these like pthreads or pthreads,
Yeah.
I put in a read lock right there.
Yeah.
That would still let other readers through. But it's not the reader.
Yes. So this is an actual implementation of a read-write lock. It does exactly what we started out to do. Let multiple readers enter. Okay. Like only ensure only one writer gets to go. And the assumption is they have done a fair job, so it will give us the property we showed here. It could be, depends on which pthread implementation is it. It could favor readers or writers. But by and large, implementations are fair in terms of how they treat readers and writers. Okay? Same with Java. If you use the read-write lock class, you will get a read-write lock. That does the same thing. Okay? So those read-write locks. Now we will look at another problem. Okay, so this problem is called the dining philosophers problem. Okay? It's a classical problem in synchronization. It's trying to do something slightly different. Okay? Here is the picture that illustrates what's happening. Okay, so the assumption is there are n philosophers. Okay, they are sitting around a table. Okay, and because they're philosophers, they only do one or two things. Okay, they think or they eat. Okay? If they're thinking, they're not eating, and when they're eating, they don't think. Okay, so that's the basic idea. And in this case, so basically when they eat spaghetti, so you have to use forks to eat, but the assumption is you need two forks, not one. Okay? And in this case, the fork is an example of a shared resource. So if you want to eat, you have to actually have two forks, so you eat with both hands. That's the way this problem works. Okay? So now, because you are sharing this resource, okay, if your neighbor is hungry and busy eating, you are out of luck. You don't have a fork. You're missing a fork, so you can't eat. You have to wait for your neighbor to finish, okay, and release the resource. In this case, that is a fork, and then you can eat. Right? So the basic idea is if you are a philosopher and you become hungry, you look at, is my right fork available? If my left fork available? If both are available, you grab them and you start eating. If either of these forks is in use, then you wait for your neighbors to finish eating, and then you contend for the fork, and you can eat. Okay, so now the question is, given this scenario, how do you actually write code that solves this problem? Okay, so you want that idea is if your philosopher becomes hungry, you don't want to starve the philosopher, literally starve in this case. Okay? So first let's see if you understand the question before we go on solution.
Philosophers pick up one fork and wait for a second, or will they only pick up a fork if they pick up?
So you are asking, should the philosopher pick up one fork, both forks, wait for both forks to be available? That's the solution, right? So we can come up with different types of solution. And if one fork is available, grab whatever is available, wait for the other one. Check if both are available and grab them both only if both are available. Otherwise, just wait for them. So that's going to be actually an artifact of how you're going to solve the problem. Okay? The problem definition doesn't say how to solve it. It just says you can eat when you have both forks. Otherwise, you have to wait. And if you are either thinking, you are not even waiting for forks. Is that clear? Now, this may look like somewhat of a contrived example, but it's actually a nice example that illustrates how processes share resources or threads share resources. Okay, so in this case, you basically have circular dependency. Okay? Each philosopher depends on his two neighbors, and then each neighbor also depends on their two neighbors and so on. So it's a nice example of what happens when you have n shared resources and n threads contending for some subset of those resources. In this case, the subset is the left fork and right fork. Okay. So now before I show you any solution, let us try to see how one can go about solving the problem. What could we do? Okay, at an intuitive level, don't tell me something about locks and sum, but I'm simply asking what would be a strategy to solve this problem. Okay, so basically, you put yourself in the place of a philosopher. What should the philosopher do? What should the code for the philosopher do? Yes.
I mean, if there, it's it depends on the form something you either support both sides of. In the beginning, like let's assume how high one are thinking. One of them decides to stop thinking and eat, so he picks up two forks that that are with his side. Let's say the people like the person then to his right decides to eat. He has to first check if there's both forks. If there isn't, he just goes back. He either goes to sleep, which is how you go back thinking, and then that logic just keeps going on. So when that person's finished eating, he puts it back down. You can either allow the processes to scope like essentially around robin style without actually having to do any special things, or you can notify people. But honestly, if the thinking is really
Okay. So, just to paraphrase what you said, fork is a shared resource. Every fork is going to get its own lock. Okay, so basically you get to get the fork, you have to get the lock on the fork. Okay, to get the lock that the fork is yours. Okay. Now the suggestion that was being made is you look for both of the forks, and if both are available, you pick them up both. Okay, that's what you said, right? And if they are not, if either one is in use or both are in use, you wait. That's one solution. Yes, basically you are saying I need two. I'm going to look if both are available. I wait. I grab them. If neither is available or one of them is in use, then I'm going to wait. One strategy. Any other strategies? Yes.
Well, I mean, if you wanted to make sure that philosophers, like once a philosopher got hungry, he didn't have to wait too long to eat. You could do something like the philosophers got a system where a philosopher on top and a philosopher on bottom are both sort of the priority eaters at that time. And if they're hungry, then the people on their side have to give up the chopsticks. And then the people on their side can just wait to see, are the priority philosophers eating right now? If not, then I can eat. Otherwise, I have to go back to thinking. And then after some reasonable amount of time, you just rotate who the priority philosophers are. You just keep doing that.
So the other suggestion is your time slots. So basically, if you get hungry during the time slot, you get to eat. And if you are hungry and it's not your time slot, somebody else's time slot, they have priority, you have to wait for your time slot. Okay, so that's actually a good solution. That's not a solution we're going to see here. But that's a solution that's used in many different cases. There's a protocol called the token ring protocol that essentially does that. The token that goes along, you wait for your turn. When it's your turn, you eat. If the token comes to you, you don't need to eat, you basically just pass it. Okay? But the token is like a global lock. Okay? So in this case, you wait for your token and it's a global lock, so you're going to eat. And the only issue with this token is if you hold that lock, nobody else gets to do anything. In this case, you should realize that if some subset of the philosophers, if every alternate philosopher gets hungry, you should be able to let them all eat in parallel. Okay? You could, of course, have more than one token in the solution that was mentioned, so long as two neighbors don't have the token at the same time, it will still work. So you should have at least a philosopher in between. Another solution is basically some sort of a token system. So what about a solution where philosophers grab forks as and when they become available, and when you are both, you eat? Yes.
If they just grab like the first fork, then each philosopher could just grab one fork and just hold that fork. Keep waiting for a second one. They would also.
Okay. So the scenario mentioned here is one that results in a deadlock, which is the next topic that's going to start after this part is done. So idea, or not the idea, but the problem with the approach is if all philosophers get hungry, okay, they all reach and say, let me grab the left fork. And they grab their left fork because all the forks are in use. Okay, now in doing so, all the forks have been grabbed, so there's nothing to do. Each philosopher is waiting for the right fork. And no philosopher is going to give in. So now they're going to starve themselves.
Wait, so are we assuming that they can't have any forks at the table? They can only have like a limited number of forks? And also, what's the assumption with the number of forks?
No, so the scenario is actually shown here, right? So there is a circular table, and you share a fork, a left fork, your left and right fork are both shared with your neighbors.
So it's exactly this. So there's the same number of forks as philosophers. and
So
they
the
don't-
same number of forks as philosophers.
So they can't get the like that philosopher across the table can't reach over and.
You can only grab. You have polite. Even if they expect a starving person. So the basic problem is if you get hungry and you just grab your left fork and everyone else does the same thing, then you're going to have a deadlock and you're going to starve. Yes.
I think the solution works better if you have an even number of philosophers, but if you have an even number, you can alternate around which fork to go for first. So you can go right, left, and then the next person goes left, right. And then you're guaranteed that if someone doesn't get a first fork, then they don't try for the second fork. But if someone does get one fork, then they will always get another fork.
Okay. So the solution here is you try to somehow randomize and make sure that if you get your left fork, you don't get your right fork and so on. You could write a solution like that. The code will not be identical for all the philosophers. Some philosophers will have to prioritize and try to get the right fork, some will have to get the left fork. You have to be somewhat careful in making sure that the scheduler is not going to defeat you, because we cannot actually guarantee in what order the scheduler will run the threads. So even though you may want to do something, it may happen in some other order, but you could certainly write it down. We would prefer something that is identical for all, but you could make them asymmetric and make it work. There is nothing wrong with that. Yes.
So you can grab the left one and then wait at different time and then grab the right one. If you don't grab it, and then you can just put both on down and try another time.
Okay. So point being made is you grab the left fork, and if you don't get your right fork, you put it down. Right? So that you could certainly do, but remember that we just want to use what we know, locks, semaphores, and condition variables. So if you actually grab a lock on the fork,
But you try at different times and then you grab it again. If
so
you
I
don't
mean
grab
there is
it,
no
then-
thing like you try it at different times. If you do a lock acquire on my left fork, and then you do a lock acquire on the right fork. If the right fork is in use, I'm going to block. So there is no such thing as I'm going to try later and put it down. And all we know is semaphores and locks. If you have the resource, you get it. If not, you block. Right? So if you could check and then retry, that would be a different problem. We don't know any such primitive as of now. Okay, so I'm going to show you some example scenarios. So this is the first case that we looked at, which is going to lead to problems. Okay, so here each philosopher simply executes this code. Okay, you basically, this is using semaphore. So you do a wait on the left fork, you do a wait on the right fork. So it's the equivalent of I do acquire my left fork, I acquire my right fork. Okay? And then if I get both forks I eat, and I release my left fork, I release my right fork, I go back to thinking. Okay? Very simple 4-line solution. Get my left, get my right. Okay? This is the problem that was mentioned where if all philosophers become hungry, okay, you may have a scenario where each philosopher executes this statement. Let's say the first philosopher does acquire my left fork. Okay? CPU scheduler says time slice is up, runs the next philosopher. It grabs his left fork. CPU scheduler says time slice is up, goes to the next philosopher. So all of them grab their left fork, and then they all come resume executing. Okay, when first philosopher runs, right fork is in use, it's blocked. Next philosopher runs, right fork is in use, blocked. All of them blocked. Now we are on deadlock. Okay, so this very simple thing says grab the first left fork, then grab the right fork. Okay, it's going to cause deadlocks if the scheduler runs them in a certain order and they all become hungry at the same time. Is that clear? Why the solution doesn't work? Any questions on this? So this is solution 2. Okay, this one is going to work. We have to understand what's happening here. So basically, what each philosopher is going to run the function test. Okay, so what we are going to do now is the very first solution. Okay, we are going to check, are both forks available? If either of those forks is in use, you block. Okay, that's the solution that is left. We said we can't just grab the left fork and then try to do the right one is going to block us. So what is left is you try to grab both or nothing. Okay, if either is in use, you block. If both are available, you proceed. And that the way you do that is you're going to basically run this test function, which is going to say, is my left philosopher eating? If the left philosopher is eating, or the right, and I'm hungry and my right philosopher is eating, or rather, if the left philosopher is not eating, because it's not equal to eating, and I'm hungry and my right philosopher is not eating. Okay, so my left neighbor and right neighbors are not eating, my forks are available. Okay. So in that case, you basically change your state to eating. Meaning you basically have grabbed both forks and you're done. Now, if not, you're going to put yourself to sleep. Either of your neighbors or both are actually eating one or both forks. So basically, say self-I signal is saying, I put myself to sleep, I'm going to wait. Okay, that's a semaphore. So now here is the synchronized pickup method and the put down method that you're going to basically use. So when you pick up, you're going to basically say, I'm setting my state to hungry and I'm going to do a test on I, which means I'm going to actually run that code. Okay? And if at the end of this I'm not eating, I'm going to put myself to sleep. Okay, so I'm going to check. If one of them is eating, then I haven't changed my state, I'm still hungry. Only both are available, I change my state to start eating. And if not, I'm going to put myself. And the put down, you basically change your state back to thinking, and you try to wake up your left and right philosophers. So when you put down your fork, you basically call the test on my left neighbor and test on my right neighbor, and if either of them had actually put themselves to sleep, then you wake them up and have them contend for the fork. Is that clear? What's going on? Okay, so I'm going to show you an example just to explain what's going on here. Okay, so let's go back to this picture. Okay, so let's assume that this is the philosopher that becomes hungry. Okay, so it's going to basically call the first function, which is pick up the forks. Okay, so it's saying I'm hungry, I need to pick up the fork. At this point in time, no other philosophers are hungry. They're all in the thinking state. So you change your state to hungry. Okay, and then you check, are both of these available? Okay, so basically you're going to run the test code. So you check, is my left philosopher eating? No. Is my right philosopher eating? No. Am I hungry? Yes. So then you change your state to eating. Okay. So then you come out of the test and you see, did I change my state from hungry to eating? In this case, the answer is yes. So there's nothing to do. You grab both forks. Okay. If one of them were hungry, then you would have waited. Is that clear? First scenario where only the first philosopher is hungry. Yes?
And so in this example, changing your state from hungry to eating is equivalent to like grabbing both chopsticks simultaneously.
Yes. In this case, when you go to eating, that means you have to grab the chopsticks. Okay, I'm going to show you another piece of code that is, this is the one that uses semaphores. Okay, so this is also using the same thing, using semaphores, but I thought I had something, no. Yeah, so here is basically the same thing that is written slightly differently. So you can see that in the test, so all of them are in the same one. So in the test, you're checking if your state is hungry, my left philosopher not eating, right philosopher not eating, you change your state to eating, which means you grab both of these. Okay? And when you put down the forks, you basically change your state back to thinking and you try to wake up. Okay? See, the left neighbor can now eat and the right neighbor cannot. So when I'm eating, if my left or right neighbor try to grab the forks and put themselves to sleep, when I'm done, I try to wake them up. Okay? So you invoke this test method for your left and right when you push down the force, which is going to go back and do this for your left neighbor and right neighbor. Okay, if now both of their forces are available, each of them changes their state to sleeping. Okay, this is equivalent of saying, I'm done eating, you tell your left neighbor you can proceed. You tell your right neighbor you can proceed, they'll recontend for the force. And if it's available, they'll start eating. And you are done. And that's the basic idea. Any questions on this? You can do this with monitors. I don't have that code here, but this is with the semaphore code. So, let me ask you this question. So, what is this up doing? That's basically a signal. I'm going to show the same code on the previous slide. Okay, so you're basically going to do a signal on this semaphore self of I. Why do you do that? Okay, in the test, you are basically checking if your left neighbor is going to eat, right neighbor is eating. If neither of them are eating, you change your state to eating. But then there is also a semaphore by signal there. Yes?
Actually, just a way of the neighbors, right? Once you go back to thinking, assume that your neighbors have locked themselves or put themselves to sleep, you signal to themselves with essentially a civil honor, it's like calling a race.
Yes. So the point that is being made is when you put down a fork, you are going to check if your left neighbor can start eating and your right neighbor can start eating. They are asleep at this point in time because they had actually done a wait on a semaphore. Okay? So let's say I am I. So I'm going to basically call, in the case where we are 5, I'm going to call my right neighbor and left neighbor. I have to somehow wake them up. That is actually happening in the test statement because my neighbor calls the test for me and then it basically wakes up. When you go signal there, it is going to wake up any philosopher that was asleep. Okay? This is only going to happen when a neighbor is trying to wake up. Okay? Because a philosopher is done eating. That clear? What's happening is why that signal is in the code. Yes.
It says waking up its neighbors.
Yeah, so what happens is there are two scenarios. The first scenario is a philosopher actually calls the test statement itself. Okay? And in that case, you check if you are hungry or if you can eat or not. If you cannot eat, you put yourself to sleep. Okay? This is what you have done. Try to pick up, call it test. And if your state didn't change to eating, you should go back to wait. When your neighbor is done, you're going to put down their fork. When you put down the fork, you see that this, when the course of putting down, you try to wake up your left and right neighbors. So this is called, this is going to invoke it for your left and right. So you go back to test and you call that signal, which will wake up your left and right neighbors if your forks are available. Okay, so that's the, so you are woken up when your neighbor actually puts down their foot if you are interested. And there's no other way to wake you up. If you are asleep waiting for a fork, the neighbor has to explicitly wake you up. Okay? That clear? Okay, any other questions? So I'm going to show you some examples of where some of these problems are actually used in practice. Yes, so I have, we have done producers and consumers, we have done readers and writers, we have done dining philosophers so far. Okay. So here are some examples. So if you look producers and consumers, that's your shared bounded buffer. Producer produce data item, put it in a buffer, consumers consume it. Okay, it's a widely used scenario. I have two examples there. So if you have, let's say, a media player, okay, you're watching a video. Okay. So internally, what's going to happen is you may have multiple threads. Some threads are actually receiving your data for audio or video or a network, okay? And then putting it into a buffer. And then there's another thread that's going to pull that data from a buffer and either display your images on the screen or send your data to your speakers. Okay? So that's your shared bounded buffer. Okay? The producers in this case are the threads that are receiving data and sticking it into the buffer. The consumers are threads that are pulling it out and rendering your video or sending it off to your screen for audio data. Okay. When you have web servers, the same thing is true. You will basically have a master thread and a slave thread. The way you write web servers is You have a thread that waits for a request to arrive on a network. Any client browser, when you try to click on the link, it sends off a request to a web server. So web server is going to have a master thread that's going to receive a request, is going to put it into a work queue. Okay? And then you have a set of slave threads. Each of these threads is going to pull a request and start processing it. Okay? So now you have a shared buffer, but the master thread is receiving requests for the network and putting it into a buffer. And the slave threads are simply pulling data from the buffer. Okay? These are HTTP requests that have come in and they start processing. And that's an example of a producer-consumer problem as well. Okay? Readers and writers, so there are many examples. Any example where you have some thread doing reads and another thread doing writes. Okay, so here's an example of a banking database where you may have multiple processes trying to read or write a record at the same time. Okay, so you walk up to an ATM and say, what's my balance? Okay, that's going to read your account balance from the database. That's a reader. Okay. Now the bank may be running a process that tries to see how much interest to give you if you are lucky enough to have a checking account that pays you interest. Okay, so that's a writer. Okay, so now you have readers and writers. So many such examples. Okay, so this is particularly prevalent in databases. You may read queries and write queries. If you operate on the same record, rather than having a global lock, it's better to read-write lock. So then the database gets more throughput. If you have multiple queries that are simply being read, let them all proceed. Rather than taking a global lock on the database and blocking all of the queries you want concurrency. Okay. So databases use read-write locks quite a bit. Okay. And dining philosophers, so this example you'll see when you have any set of processes that share resources that have to grab locks on the same resources. So when you do backup, you are going to see this because there will be processes that want to lock certain files before you want to backup and so on. If you're doing travel reservations, you want to do this also. Okay, you may have, let's say, every time you go to Expedia or any of these websites, if you're trying to do a reservation, they go off to airline systems and then try to retrieve reservation information. Okay, if you go to multiple systems and retrieve it, you will actually have to get locks so that you do this in some reasonable way. You may be holding multiple locks at the same time. Okay? And there may be many such instances, many such reservation requests in process. Each process that's trying to do a reservation request is an example of dining philosophy, trying to grab multiple locks at the same time. So many such examples exist in the real world where these small examples we have looked at here map onto real world problems. Okay, so it's good to know how to solve them in the abstract. That way when you encounter these problems, you know how to actually solve it for those things. Okay, so I'm going to end this here today. We'll start with deadlocks next time, and also I'm going to do a review of the exam next time.